Hello, my name is Ursula McKnight. I'm an assistant professor in the Department of Environmental Engineering here at the Technical University of Denmark. And today I'm going to be talking about risk assessing water quality under stress. The environmental status of a water body is highly influenced by the characteristics of its catchment area. For example, climatic conditions such as precipitation influence water flow. Soil type influences the mineral content of the water, and all of these factors influence the natural range of species or biodiversity. For over 2,000 years, humans have been altering river basin habitat for land drainage or urbanization, flood protection, water abstraction, and in particular, over the last 200 years, we've added to this disruption with pollutant discharge, for example, inadequately treated sewage, and the application of fertilizers and pesticides to agricultural fields. These activities have led to major changes in river processes, predominantly with respect to flow, the transport of particulate matter, and the migration of species. These activities have additionally led to major problems with quality of our water resources, both groundwater and surface water quality. In recognition of this, the European Union passed the Water Framework Directive in 2000, a visionary planning tool setting targets to integrate water quality and ecological status. 2009 saw the first reporting of river basin management plans, with member states delivering a massive amount of data on status, pressures, and measures, which somehow indicates that we understand how to evaluate environmental status. If we take as an example how we evaluate ecological status, we identify three aspects. First, we look at the health of our biological elements, for example, fish and benthic macroinvertebrates. Then we look at the physicochemical conditions, and finally, the hydromorphology. However, water bodies are not improving quickly enough. If we take a closer look into the data, it's been identified that we have ambiguous results due to data gaps and inconsistencies across member states, which really points to a suboptimal knowledge base dealing with methodological implementation. Notably, rivers and transitional waters have been identified as having poorer water quality than lakes and coastal waters. Let's take a look at a typical Danish catchment to see if we can understand why. This particular catchment, which is typical for a Danish setting, has around 80% agricultural land use, as you can see here. If we add water supply well fields is in the green circles, and on top of that we have contaminated sites such as landfills, also often placed close to surface water. So there's really a massive potential for contamination at the catchment scale. And rivers somehow are the place where all of these pressures are coming together. In risk assessing water quality, we need to take a source pathway receptor approach in order to link sources to impacts and ultimately prioritize cleanup measures. In doing this, humans really like to compartmentalize things, but we need to take care with this because we need to understand, in particular when we're talking about the hydrologic cycle, that these compartments are connected. In fact, surface water, such as rivers and streams, are really complex environments that act as a footprint for all of the activities in the surrounding area. When we talk about impacts on water quality, we distinguish multiple contaminant classes. For example, we can have chlorinated solvents coming from point sources such as contaminated sites, or we can have pharmaceuticals discharging from wastewater treatment plants. And then we also have diffuse source impacts such as pesticides and nutrients from applications to agricultural fields. This is really large-scale pollution. If we take a look at our research with respect to pesticides, we've been trying to characterize the occurrence of pesticides in streams. And it's really a very, very complex picture for pesticide entry to surface water, making it very difficult to identify the sources of the pesticides impacting aquatic ecosystems. And we've also found that we're lacking methods to properly characterize ecological health. But this is just the tip of the iceberg. In fact, over 1,000 pesticides are sold annually in Denmark. And really, we're really just characterizing a fraction of these when we're looking at the status of our water bodies. This brings up also the point of persistence of legacy pesticides. So as we're phasing out these compounds, we stop looking for them, but that doesn't mean that they're not still present in the environment. We also have a lot going on with respect to contaminated sites investigation. which of course impact groundwater, but these can also impact surface waters. And it's really a challenge to quantify contaminant mass discharge and impact on streams. We're lacking particularly field methods capable of dealing with temporal and spatial variability. And here I'm talking about really complex flow patterns at the groundwater-surface water interface. There's always the issue of the quantification of uncertainty, and of course, accounting for multiple stressor conditions when trying to quantify ecological health. In dealing with these issues, we've been developing a quantitative assessment toolbox, of which I'm going to talk about two aspects today. The first is on contaminant mass discharge, which is a function of both the flow and the contaminant concentration. It's not enough just when we're talking about ecological quality assessment points, it's not enough just to look at concentrations if we want to connect impacts to their sources and ultimately prioritize the remediation. So we really need to look at contaminant mass discharge. For this, we've been developing a suite of field methods using both indirect and direct measuring tools, and we've been applying modeling approaches, both numerical and analytical systems. The second aspect of our assessment toolbox deals with chemical and ecological status. The traditional way of doing this is to look at individual chemicals on individual species. So we take, for example, Daphnia magna, and we put them into a tank, and we apply our favorite contaminant of concern, and we produce these dose-response curves. However, if we take a closer look at reality, we can see that we really have contaminant mixtures, and they're not just impacting individual species. So we need community assessments in order to deal with this. Some new methodologies are being developed, and we've been applying them to our field sites. Just to give an example of the type of information that we can get from these new methodologies, which are attempting to link actually the toxicity of chemicals to the ecological status. I'm showing a figure here which shows predicted toxicity of pesticides. And the first piece of information we can get out of this is that we were able to quantify the contribution of legacy pesticides to toxicity. We've done this by plotting here pesticides which are still permitted for use in Denmark against the entire cocktail that we screened for in our water samples. And we can see that in all cases, regardless of the sample type, when we include the legacy pesticides and metabolites, we get increases in the ecotoxicity. We were also able to quantify the contribution of different pathways to toxicity. Previous research has suggested a threshold of -3 for effects on acute observed effects on community structure. And so we were able to see that it's actually the pesticides bound to suspended sediment that are driving the ecotoxicity out in our streams. So the take-home message is really that when we're talking about water resources management, this is one interconnected resource. So we need to deal with water quantity and water quality at the same time. We need to take care when compartmentalizing impacts to both groundwater and surface water, as these are also interconnected. And that also goes for both the urban and natural landscapes, which can really affect each other. With respect to the chemical footprint, this is really a very complex picture. And in dealing with this, we need mass discharge approaches to properly link sources and impacts and prioritize remediation efforts. Finally, we really need to take a holistic perspective when we're looking at impacts to ecosystems. We're really dealing with multiple stressor situations here, and we have chronic low-dose contamination with the additional seasonal acute pulse contamination going on, and we need methodologies that can deal with this situation.